Okay, we've got a couple examples here of the E1, E2, Sn1, Sn2, that whole mess of trying to figure out which reaction is going on. So we'll have to figure out which one is going on, what the products are, etc. Okay, so in the first case, here we've got this organic compound. We see a stereocenter, and so they're kind of teasing us to make us think, oh, maybe this is a Sn2 or something, or invert configuration, which it could be, we'll see. This is called like a sulfonate group or a mesylate group. Sometimes it uses a protecting group. What you need to know about it is a really good leaving group. So this works well for us. We've got an alcohol here, so it's not a good base. So we're starting to think like solvolysis, probably Sn1 or E1, because we just don't have that strong base or good nucleophile. We've got low temperature. So again, that pushes us to the Sn1 direction. And so we've got a good leaving group. We've got alcohol, makes us think Sn1 or E1. We've got low temperature, which makes us think Sn1. And we've got a tertiary carbon, 1, 2, 3 carbons there. So because of all that, I'm thinking it's Sn1. This is unlikely going to do an Sn2. This will force the Sn1, low temperature will force the Sn1. Now because it's Sn1, we're going to end up with a racemic mixture that is not optically active. So let's see what it'll look like. We'll have this central, we'll have the methyl group up there, we'll have an ethyl group, we've got a propyl group right there, and then the right hand side what it substitutes for, which is going to be this O, this right here. So if I circle this part right there is right there, okay? So we just substituted for it, was a racemic mixture, so this part just stuck right on there without the hydrogen. It's a loss in the mechanism. Alright, let's take a look at the second one. So in this second case, we've got a little different situation here. We've actually got two leaving groups here. So one we'll have to decide which one goes. These are both secondary carbons, so it really could do anything. We got the polar aprotic solvent, meaning it doesn't have extra protons to give, but it's polar because it's acetone. So that makes us think the Sn2 direction. We've also got a good nucleophile here. It's not good nucleophile, makes us think Sn2. We don't think E2 because it's not really a strong base. If this was an oxygen here, we'd probably start to think E2. But they forced us into Sn2 with the solvent and with the good nucleophile that's not that strong of a base. So now we have to decide, is it going to substitute top or bottom? Well, it could probably do both, but because of these two methyls here, it's a little more sterically hindered at the top, so we're thinking it's going to more likely substitute on the bottom. Now remember that the Sn2 also inverts the configuration. So when we draw this out, I'll draw the cyclohexane. We've got the two methyls, we've got the bromine on the top, so that's all the same. It's the bottom that we're going to mess with. Now it's going to be going away from you, so I'm drawing a wedge. I'm going to draw a C, S, CH3 at the bottom, but going away from you because the configuration inverted. So again, we had in the first case an Sn1, in the second case we have a Sn2. So the second case does have stereochemistry, so it is optically active, where the top case was racemic. Okay, now let's look at this third one. We've got a methyl group here, so it's in the primary category, but a special category. Whenever we see this, it has a good leaving group. The only thing we think of a methyl is a substitution, Sn2. There's really nothing else it can do. It can't have a primary carbocation, just a high energy move, and so we're expecting it, this whole sulfur group just to substitute on, even though it's an okay nucleophile, could be better, it's not really a strong base, but there's really no choice in this situation. So we're going to go, this S, well let me write it like this. We'll have the CH3 2S with another CH3 on it, like like that, and so that'll cause this to have extra positive charge. And just to simplify it and write it a little bit different, you could write CH3 positive, and if you want, you'll have to see with your instructor. Sometimes they have you write the I minus right there. That's totally fine. You'll want to see with your instructor if you need to write the leaving group as an additional product. And if you're into that, make sure you're doing it too. So this last case was also an Sn2, which is a pure substitution.